Dear colleague, this is a good opportunity to talk about transportation because I know my very good friend Chino was very much interested in transportation, and we had a lot of different talks in the past regarding that. It is really sad that Chino is not more with us. Anyway, I'm going to talk to you about the fission of palladium thin films in hydrogen atmosphere under laser irradiation. Actually, this work is a repetition of the one made by Ubaldo Mastromateo in 2016. And he did a very simple experiment where he directed a laser beam on a thin film of palladium deposited on a silicon oxide substrate in both hydrogen and deuterium atmospheres. He analyzed by SEM, and he showed that there were many new elements that appeared. I was very lucky that he gave me 2 of his samples so I could do the same experiment. After waiting for many years, recently I did the same experiment with hydrogen and deuterium. Both experiments lasted 3 months. I used a laser that's a pointer laser, 5 milliwatt, 650 nanometers, the red laser. You can find the publication by Mastromateo in the Journal of Condensed Matter Nuclear Science. What were the experimental conditions? The samples were 1 square centimeter, again a silicon substrate. There was a thin chromium adhesion layer so that the 350 nanometer palladium film could adhere very well to the substrate. The laser was 5 milliwatts at 650 nanometer, and I used a quartz chamber. It was actually a quartz tube, and evacuated it and filled it with hydrogen and or deuterium at a pressure of approximately 2 bars. Both experiments lasted 3 months. Here you can see a setup of the system. The tube is mounted on a CF35 flange, and the tube is 30 centimeter long, 3.5 centimeter diameter. The laser beam is on top of the tube, and there is a valve that can pump and insert the gases. In this view graph, you can see how I mounted it. Actually, the sample is mounted on an 8 millimeter stainless steel rod, and the sample is attached at the top, and the laser beam is a very simple laser that I bought for €4. To do the analysis, we use a scanning electron microscope, a geol microscope, and we had also, it's a very new high quality microscope, high resolution. It's coupled with a X-ray spectrometry to analyze the composition. First, in hydrogen atmosphere, we observed very interesting spot. There was a hot spot. The image shows this. It's about 200 micrometer in diameter. It's amazing to see that, but when we analyze it, we saw that there are 3 regions. The center region, which is very dark. There is another region, which is a kind of a circle around that one, slightly twice larger. And then the gray area around it without any change, it seems. We analyzed 3 spots in the middle, 3 spots in the second circle, and 3 spots in the gray area. What's interesting is the analysis of the 3 central points. In the 3 central points, we find nitrogen, oxygen, sodium, aluminum, silicon, phosphorus, sulfur, manganese, iron, nickel, zinc, palladium. And palladium is very little. In point 1, we have only 0.25% of palladium, which is very little. What's surprising is there is nitrogen. I mean, nitrogen cannot come from nitrogen. Could be a leak from the system or from a contamination later on in the air, because it's hard to dissociate nitrogen. N2 is a very stable molecule, and you cannot deposit nitrogen like that. Even with a laser beam that's so weak, a 5 milliwatt laser on a 4 square millimeter diameter spot, it's very little power. There's no chance you will dissociate nitrogen like that. Also, there's a lot of oxygen. It doesn't make much sense because there is oxygen in air. You can imagine a contamination later on in the atmosphere, but it's very unlikely. Now, some of the elements are very low-level elements, like silicon, but that could be substrate, phosphorus, 0.07%. But there are a lot of elements that have large quantities, like sodium, 6.44%, iron, 294, nickel, 8.83. So these are definitely good elements that were not there before. If I look at point 2, it's about the same composition, slightly more palladium, 7% instead of 0.53, and point 3, about the same again with 7% palladium. I think something has happened. Now let's look at the second ring. First, before I show you the spectrum. These are the 3 spectra superposed where you can see different elements, point 1, point 2, and point 3. The peaks are clearly visible there. There's no doubt they exist. Again, this is spectrum number 2 in details. You can see all these peaks. Even you see the iron peak, the nickel peaks are clearly visible here. This is a detail showing that the aluminum peak, silicon peak, phosphorus peak, sulfur peak, palladium peaks are there. Now if we analyze the 3 spots on the ring, you can see the new composition. And there's more palladium this time, 17%, 55%, 25%. So it seems that the reaction is less effective in this part of the spot. Some of the elements are below the 1% limit, but they are probably there anyway. Again, we have nitrogen, oxygen, sodium, and nickel that are there. You can see now a spectrum of the 3 spots superposed, showing the appearance of these different elements. Now, 3 spots have been analyzed outside of the hotspot, and here you can see that there's almost nothing. 95% palladium, 96% palladium, 94% palladium, and some oxygen. The reaction is almost not visible. Could be that the oxygen is due to contamination. Here are the spectra of these 3 different points. Now I've done the same experiment in the deuterium atmosphere. There, I couldn't find any hotspot. We tried to analyze different places on the surface, but couldn't find any hotspot on it. The composition shows mainly palladium, 99.78%, traces of oxygen, some silicon. It seems that outside of the hotspot, nothing happened. This is the spectrum showing the palladium peak. Okay. Definitely something is happening. Everything is in the hotspot. And I know that Maestro Matteo, when he did his experiment, he did also a blank where the wafer was in the hydrogen atmosphere without laser beam. And he also saw some transmutation there, but less than with the laser beam. So the laser beam is doing something, but maybe just hydrogen and palladium are reacting by themselves. If you look at here, you can see in red, this is palladium, and in yellow, all the elements that have been measured. You can see that they are all lighter than palladium. So that means we are producing fission and not fusion. The conclusion would be that palladium and hydrogen plus light produces fission. I have tried to develop different reaction mechanisms. For instance, if you take palladium, you can split it into chromium and titanium. This has been shown by Mastro Matteo, but I didn't detect it. Palladium could produce manganese and scandium, but I didn't detect scandium. But palladium could produce iron and calcium. I measured both. Palladium produced cobalt and potassium. But this is only Mastro Matteo. I didn't see it. Palladium produced nickel and argon. This is very possible. I've seen nickel, but argon is impossible to detect because it's a gas. Palladium will produce zinc and sulfur. This has been observed. Palladium could produce molybdenum and beryllium, but I've not detected beryllium. Another option would be to produce calcium and 2 atoms of aluminum, silicon and 2 atoms of sulfur, zinc and 2 atoms of oxygen, chromium and 2 atoms of sodium, sulfur and 2 atoms of phosphorus. And another option would be to have palladium giving oxygen and phosphorus, nitrogen and sulfur. If you look at these reactions, and if you check isotope per isotope, some of the reactions will produce 1 neutron. Some are not possible. So in the future, we will plan to do 2 things. First, before I have to talk about deuterium. With deuterium, I didn't detect any element. Mastro Matteo has detected less elements, but he detected some anyway. Conclusion. Okay, with hydrogen there is transmutation. There is fission of palladium. That's pretty much sure. With deuterium, very much less reactions, and I didn't detect any. However, in the meantime, since the experiment has been terminated, I have placed CR39 to detect neutrons, because as I was telling, due to the fission reactions, there are extra neutrons, and we might be able to detect these neutrons. The neutrons are now under analysis. Isotopic analysis by SIMS will be important to see if there is a isotopic distribution that is different from the natural distribution of the elements. Hopefully with all these measurements we'll have a better understanding of what's been happening in this reaction. I think this is a very simple experiment that is possible, many people can do. It could be like a lab rat for people interested in doing some simple work on low energy nuclear reactions. Thank you very much for your attention, and we will talk later on the discussion group.